Okay, so let's talk about a weird paradox. Something that, well, it underpins our entire existence. Think about the chair you're sitting on, the air you're breathing. It's all made of atoms. And we all learn that opposites attract. But that simple rule, it hides this terrifying mystery. A mystery that says none of this should even be here. So let's dive into that incredible story. So here's the big problem, right? Every single atom has this dense positive nucleus, and then you've got these tiny negative electrons just zipping around it. And if opposites attract, well, what's stopping that electron from just crashing right into the nucleus? Why doesn't everything just, poof, collapse in on itself? I mean, why are we even here to ask the question? All right, to figure this out, we gotta look at our first suspect, the classical atom. This is the version most of us probably remember from science class. You know, it seems super simple, kind of elegant, but, and this is a big but, it has a totally fatal flaw. This model comes from Ernest Rutherford, and he pictured it like a teeny tiny solar system. You've got the nucleus playing the part of the sun, right in the middle, and the electrons are like planets, orbiting around it. The only difference is, instead of gravity, it's the electric charge that's holding everything together. It's a really neat picture, right? It feels right. And it makes perfect sense for a second. But then you bring in the actual known laws of physics, and the whole thing falls apart. Turns out there's this inescapable rule that turns that neat little solar system into a ticking time bomb. Yeah, see, according to Maxwell's laws of electromagnetism, and these are like the bedrock of physics, any charged particle that's accelerating or even just changing direction, which is exactly what an orbiting electron is doing, it has to radiate energy. It's not a suggestion, it's a law. It just has to. So what happens when that electron starts losing energy? Well, think about a runner getting tired. It starts to slow down. And as it slows, that pull from the nucleus just gets stronger and stronger, too strong to fight. And then it starts that catastrophic death spiral right into the heart of the atom. And you might be thinking, okay, how long does this take? 1,000,000 years? 1,000? Nope, not even a second. According to classical physics, every single atom should collapse in less than a nanosecond. So the fact that you're hearing this, and I'm saying it, is pretty solid proof that something is deeply, deeply wrong with this whole picture. So basically, physics was broken. The model didn't work. And then this Danish physicist, Niels Bohr, comes onto the scene, and he has this totally radical idea. He didn't really explain why the atom was stable. He just sort of rewrote the rules of the universe to make it stable. So Bohr came up with this ladder model. He said, imagine the electron's orbits are like rungs on a ladder. An electron can be on the first rung, or it can jump up to the second rung. But, and this is the key, it can never exist in that empty space between the rungs. It's just not allowed. And by locking them into these special fixed orbits, they were magically forbidden from losing energy and spiraling to their doom. Now, this was a brilliant fix, don't get me wrong, but it was kind of a patch, you know? It worked on paper, but it didn't answer the real question. Why? Why are the orbits fixed? Why does the universe even have these bizarre and visible ladder rungs for electrons? The real answer? Well, it was about to get a whole lot weirder. And that brings us to the final reveal. The solution came from a French physicist named Louis de Broglie, and he proposed something that honestly sounds like it's straight out of science fiction. He said, what if the electron isn't a tiny little dot zipping around? What if it's actually a wave? So you gotta throw out that old image of a tiny orbiting dot. Instead, think of the electron as a standing wave, a vibration of energy that's spread out, wrapping all the way around the nucleus. And here's the cool part. For that wave to be stable, for it to not just fizzle out, it has to fit perfectly around that circular path. It's kind of like a guitar string, right? When you pluck it, it can only vibrate at certain frequencies to make a clean note. Any other frequency, it just dies out. It's the exact same idea for the electron. The wave can only exist in these specific orbits where its wavelength fits a whole number of times. And boom, those are Bohr's ladder rungs. It's not some random rule he made up. It's a direct consequence of the electron being a wave. Okay, so the electron is a wave. That explains the fixed orbits. But that's still not the full story. There's one final, crucial piece to this puzzle. A quantum rule that is so bizarre, so powerful, that it's literally what makes our existence possible. And that rule is the famous Heisenberg uncertainty principle. What it says is basically this. There's a fundamental limit to what the universe will let you know. It's a trade-off. The more you pin down an object's exact position, the less you can possibly know about its exact momentum, where it's going. And it works the other way too.
So how on earth does that save the atom? Well, let's picture that electron getting really, really close to the nucleus. As it gets closer, its location becomes more and more certain, right? It's being squeezed into this tiny, tiny space. But the uncertainty principle says, whoa, hold on. You can't have that much certainty about its location for free. The universe demands a trade-off. And to pay that price, the electron's momentum, its speed and direction, has to become incredibly uncertain, extremely large. So, as that electron gets closer to the nucleus, its position gets super certain. Step 2, to balance the cosmic books, its momentum has to get wildly uncertain. We're talking a huge, unpredictable range of possible speeds and directions. This means it gets this massive, energetic kick that just pushes it right back out away from the nucleus. It acts like a quantum shield, a force field that physically prevents the collapse from ever happening. And that is the absolutely mind-bending answer. The reason your chair exists, the reason we exist, isn't because of some nice, tidy little law. It's the opposite. Everything is stable because the universe at its very core is fundamentally uncertain. It's fuzzy. And that very uncertainty is the only thing stopping everything from collapsing. Which really leaves you wondering, right? If something as basic as the stability of matter, the fact that things exist, is guaranteed by a principle as weird as quantum uncertainty, what other incredible cosmic truths are just waiting to be discovered, hidden in the bizarre and beautiful fabric of reality?